All right, so our next topic is normal distribution. Okay, this is going to tie in with the idea of standard deviation that we looked at yesterday. Okay, so the idea of what normal distribution is it's basically just the idea that with certain things, especially things like that come up in the real world, you're going to see that data will be spread out in a particular way that tends to show up a lot. Okay, so let's think about an example really quick. So, say I gave you guys all a quarter and asked you to flip it 8 times, okay? And then record how many times did you get heads, how many times did you get tails, okay? Well, if you think about what that's going to look like, if we were to make, say, a histogram of what this looks like, right? If you're doing the coin, you're going to flip it 8 times, right? And it's a 50-50 shot. So, when you look at how many times is heads going to come up 4 times, right? You would expect that to happen fairly often, right? So you're going to expect that the number of times that happens will be fairly high. Okay, if you were going to get 5 heads or 3 heads, though, that wouldn't be unusual, right? Flipping a coin 8 times, not being perfectly 50-50, that's not unusual. It's going to happen probably a little bit less often than the 4 times does, but it's still pretty close. Okay. Now, if we were going to get 2 or 6 heads when you flipped a coin, that's going to be less likely. Out of 8 flips that you only get heads twice, right? Or that 6 of them are heads, that seems like it's going to be a lot less likely. So we're going to see that, okay, we're going to have a lot fewer of those instances that come up. Okay. And then if we were going to have 1 head or 7 heads, again, flipping it 8 times and only getting heads once, that's going to be very unusual. Okay. And to not get heads at all or to get heads every single time, that's going to be even less usual, right? So what kind of happens with your data is you get this thing called a normal spread, okay, where you get the most in the middle, and the farther you go away from that middle spot, the less likely something is to happen. Okay, and what we're talking about here, we're going to talk about something called the normal curve, which is basically just saying, okay, well, if I look at this graph sort of follows this curve, and that's what we call the normal curve. Okay, so you're going to see these things sort of show up anytime that you have something where you have like a process that's run by a machine, like something that creates, I don't know, candy bars, a machine that makes candy bars, and you're measuring the weight of the candy bars. You're going to see most often that the average will show up, and the farther away you get from the average size, the less likely that'll be to happen. Okay, so that's an example that you're going to see this. You see it a lot of times in nature with like when you're measuring the heights of people, or if you're measuring like, I don't know, foot size or something like that. So you're going to see these things show up on the size of a pine cone, things like that. Okay, so this happens very, very often enough that we call this a normal distribution. Okay, so here's that curve that we just talked about. Okay, and the cool thing about this is that it's sort of a model that you can use to make predictions of how likely something is to happen. Okay, so when we look at the normal curve, first you need to know that this little symbol right here, that stands for your mean. That's the Greek letter mu. All right, and then your standard deviation is this symbol right here. Okay, so it's like a little O with a little line coming off of it, like a cursive O. So that's the standard deviation that you talked about before. Okay, so average, standard deviation. Okay, when we look at this graph, we see that the area underneath this blue curve is 1, which is like the equivalent of 100%. And then these areas are broken down by percentages. So you can kind of see on this one that this section right here, that's 34% of your picture. And that's going to be where 34% of your data lies. Okay, so if we were talking here about heads and tails, my average number of heads and tails would show up here, and 34% we would expect to be within 1 standard deviation of the mean. Okay, so there's 34% in this chunk, 34 here, there's 13% here, 13% here, and you can see the rest of these numbers. Notice that once you get really far away, it's a teeny tiny amount, right? That's not even 1%. That's a lot less than 1%. So that's a very unusual thing to have happen. This graph is the exact same thing except in chunks. Okay, well, why are we talking about these chunks? Because the middle thing that shows up is going to be your average, And then these little vertical blue lines, those are measurements that are 1 standard deviation above or below the mean. Okay, so if my mean is 10, this would be 10. And if my standard deviation is 12, then this would be 10 plus 12, so 22, plus another 12, so 34, plus another 12, so 46, right? And then anything that would show up that would be above 46 would be in this little area out here, and that's very unlikely. Okay, so 68% of your data lies within 1 standard deviation of the mean, 95% within 2, 99.7 within 3. That's a typo. 3 standard deviations of the mean. Okay, so that's kind of what you can expect to see. You are going to need to be familiar with this table. Okay, I would recommend you memorize these 3 numbers rather than all of these numbers. But that's just me personally. Because if you know that this is 68%, it's pretty easy to come up with a 34. Okay, but that's just a suggestion. Okay, so let's look at how we're going to build these things. So here's how you're going to make a standard deviation curve. So I'm starting with just a regular old number line. The middle of my number line, I want to be my mean. You need to make sure you know which symbol is which. This guy's your mean, your average. So that's 10. Then I'm going to go equal jumps of whatever your standard deviation is, 3 in both directions. So I'm going to go to 13, 16, and then 19. Okay, so those are my 3 standard deviations. And then in this direction, 10 minus 3 is 7, 4, 1. So I went 3 in each direction. And then to draw the curve, you want the first one to be nice and tall. The next one is going to be still pretty tall, right? And you want these to be about equal height. They're close to equal height. All right, so the first one's going to be fairly close. And then after that, you're going to see kind of a big drop off in the height. And then the last ones, these guys are going to be super tiny. Okay, so I always make those bars first and then use that to draw my curve. It's a little bit tricky the first couple of times you try it, but you'll get more used to it. Your goal is that it should look like this. Okay, so that's what you want it to look like. So this guy over here, same deal. My mean is the 38, so that goes in the middle. And then I want 3 standard deviations in both directions. So 48, 58, 68. This would be 28, 18, 8. Okay, top sections, the tallest. The 2 on either side are just a little bit shorter. Then you get kind of a big drop for the next standard deviations. And then these ones are really just tiny. And you can kind of use that to draw your curve. Voila. Okay, so that's kind of what your normal distribution looks like. Again, the goal is to have it look like this. I think mine's maybe a little bit off, but you know, try to be as close as you can. Okay, great. So we've drawn these little things. How is this helpful? Well, let's take a look at an example. So we've got scores for a state's peace officer standards. That's kind of like a police officer. It's a little bit different. You can look it up if you're interested. So this training test, the scores are normally distributed with a mean of 55 and a standard deviation of 12. The scores range from 0 to 100. So this is an example of a test that they're giving where a 100% is not necessarily what you're shooting for. A similar idea for you guys would be the SATs, right? When you take the SAT, your goal is not to get a 1600. It's not like you have to get like a 1600 in order to get a really good score, right? They're grading you off of how you compare to other people. And that's what happens here. So for this particular test, they're saying, well, this is the average score, and this is your standard deviation. So where do you fall in the comparison of other people? Okay, so let's take a look at what this is going to look like. I'm going to start by making my graph here. So my mean is 55 and my standard deviation is 12. So I'm going, again, 3 in each direction. So that'll be 67, this will be 79, and then that'll be 91. 3 in this direction. I made too many lines, right? Will be 43, 31, and then 19. I don't need that extra line. That was a mistake. All right, so tallest one. These guys are a little bit shorter, but the same height. These guys are a lot bit shorter, but the same height. And then these guys are just tiny. And there's my curve. Okay, so now this question asks us what percent of the people taking the test are going to be between a 43 and a 67. So that's these guys right here. So what percent of people are going to be there? Well, that's 1 standard deviation in both directions from the mean, right? and that's going to be 68% of your data. So this is going to be 68% of the people who take the test. So 68% of the people who take the test are going to score between a 43 and a 67. Right? Now for part B, there's an agency that will only hire applicants with test scores of 67 or greater. About what percent of people have scores that make them eligible? Okay, so if we look at our graph again, so here's 67, that's 1% above the mean. Okay, and if we want them to be higher scores than that, that means that I need anybody in all of this section here, right? Okay, so we need to figure out all of that together. So the easiest way to do that is to kind of break it down from here. 67 was 1 standard deviation above the mean, right? The mean plus 1 standard deviation. So I want these sections here. So the first one is 13.5%. The next one's 2.35%. And the next one's 0.15%. So what I'm going to do is I'm going to add up all of those percentages. So that adds to 0, carry the 1. This is 6, 7, 8, 9, 10, carry the 1. So that's 16. So 16% of people. Okay, so when this test agency or this agency says they only take people with a 67 or greater, that means that they're only taking the top 16% of applicants. Okay, so that's actually, although it's 67, you're kind of thinking in your brain like, wow, that's barely passing. For this particular test, that's actually a really good score. That puts you in the top 16%. Okay, so that's kind of the idea of what a normal distribution is. Now, here's where the issue comes in. What if this agency had said, you know, we're only going to take people with a score of 70 or higher? Well, if the score is 70, that doesn't fit well on my table. So what am I going to do with that? How am I going to figure out for a score of 70 where I've got these percentages? I can't just do something where I figure out, okay, well, 70 is about, you know, whatever percent of the way between these two and then come off here, because that's not how these percentages are broken up, right? It's not that each section is equal. So I can't just break it down that way. And that's where our next piece comes into play. Something called a standard normal distribution with this thing called the z-score. Okay, so basically what this is it's a way that you can just change the data to match specific numbers so that they're more easily comparable. Okay, so example, these two graphs that we made here. Say these were 2 different tests that people took to apply for this agency, right? Well, when we look at this, getting a 13 on this test is the equivalent of getting a 48 on this test because they're both 1 standard deviation above the mean, right? So you have the same number of people that you beat out in either score or either test with those scores, right? So what the z-scores do is they say, okay, well, instead of using the numbers 13 and 48 to describe those numbers, I'm going to use the number 1 for both of them because they're 1 standard deviation above the mean. And then I'll use a 2 for the 16 and the 58 since they're 2 above the mean, and a 3 for the 19 and the 68 because those are 3 above the mean. Okay? These guys, those are 1 below the mean, so I'm going to give them -1. These guys will be -2, and those guys will be -3, which makes the mean 0. Okay, so the mean is 0 standard deviations. And that's what this is. So it's the exact same thing, but we basically take the numbers that we had before and we convert them into this easier scale to make it easier to compare numbers. Okay, now here's one of the key pieces that you are going to need to have here. Right here, there's a little formula kind of buried in this paragraph, how to calculate a z-score. So to find your z-scores, what you need to do is you take x, which is whatever your data score is, so whatever thing you're looking at. Okay, so that's the number you're looking at. You subtract from it, that's mu, that's your mean, and you divide by the standard deviation, sigma. Okay, so you take whatever number you're testing, subtract the mean, and then divide that by the standard deviation. That gives you your z-score. Okay, and then we have these things called z-score tables. Okay, there's a bigger one of these that you're supposed to be printing out from your agenda for the day. Okay, what the z-score table is it says, okay, well now, once you convert to this z-score, you now can use this table to figure out what the exact percentage is. So if I have a z-score of 1/2, I want to know where that is. Well, I know it's somewhere between 50% and 68%, but I don't know exactly where. That's what this table tells you. You can look at this table and say, okay, well, here's a z-score of a half. Oh, well, that's 69% of data. Okay, so that's the point of what this is. I said before that this would be 68%. It's not. That was a mistake. 68% is between these two. That's not 68%. I apologize. Right, so that's kind of what this allows us to do. Okay, so let's take a look at, first of all, how this table works. So again, you've got this table that was posted with your thing. The first thing that you need to notice is that these z-scores listed on the side, on one part of this table, they're positive. On the other part, they're negative. Okay, so make sure that you're on the right side, depending on what you need. Okay, and all you're gonna do is you use this table to find whatever number you want. If I wanted a z-score of 0.5, then I'm gonna come along here, I'm gonna find, okay, well, here's 0.5, and I don't need any decimals after it, so here's where 0 is. There you go, that's my percentage. Okay, if we wanted a z-score of 1.25, well, then I would come down here and find 1.2, and then here's that extra 5 that I need, and then you just follow the table to where they meet up, and there's your percentage. Okay, so that's how this table works. So let's do an example, okay? So here's an example talking about babies. So the weights of infants at birth are normally distributed. You got this for your mean and this for your standard deviation. We choose a kid randomly at birth. What are the chances that randomly chosen kid is going to weigh this much or less? Okay, and that's a key thing, weighing or less, because your your z-score table always gives you the percentage up to that point. So just like we'd say that here, right, at the standard deviation of 0, this is 50% of your data, right? So 50% is below that. What your z-scores do is they tell you what percentage is always below. So like if this were a test, what percent of people did you do better than? Okay, so we're gonna figure that out for this guy. Okay, so we got this baby, and we know to calculate the z-score, that's gonna be our first step. So to calculate the z-score, you do the number that you're testing, right? So the number I'm testing, the baby I'm testing here is that 5170. I subtract the mean, the 3270, and then divide that by the standard deviation of 600. Okay, so I'm gonna grab my calculator. All right, 5170 minus 3270, and then divide that by 600. So this is a z-score. I'm gonna round to the nearest hundredth because that's what our table goes up to. So my z-score is 3.17. Okay, all right, so that's my z-score. Now I'm going to take that number and I'm going to go to the table. Okay, not this guy. I'm going to use the one that I printed out. So make sure you're on the positive side. And I want 3.17. So here's 3.1. Okay, and then up here, there's the 7 I need after it. So I'm going to follow this over to where those meet up. And it's at 0.9992. Okay, so this is 0.9992, which is 99.92%. So what does that mean? It means this randomly chosen baby is fatter than 99.92% of other babies, right? So this guy, he's kind of a pudge, right? To give us a little bit of context, if you think about how much does your typical baby weigh, right? Well, I did some conversions. Okay, so this 3270 grams, when you convert that into pounds, is about 7.2 pounds. That's about a typical baby, all right? Versus this baby that we tested this baby that was 5170, right? Come on, convert it, right? Okay, well, it's not doing the whole thing, but there you go. That's an 11.4 pound baby, okay? So this baby that we tested was 11.4 pound baby. That is unusual. That's a fat baby, okay? So it does make sense that they'd be heavier than almost all other babies, okay? So that's what z-scores do. And it's just a way that you can kind of compare different sets of data and that you can find these in-between values that aren't exactly on these lines without having to do a ton of crazy work. All right, one last thing, just to reiterate this, you've looked at this before in a previous lesson, okay, but these are what your non-normal distributions are going to look like. So in normal distribution, we call bell-shaped because it's supposed to look like a bell, right? Okay. All right, so that's what this guy is, where your mean is exactly in the middle. But then we also have data that can be skewed left or right. This is left skewed data. This is right skewed data. Personally, I always tend to get that backwards. I feel like this one should be right. But the idea is kind of that the data has been pulled to the left or pulled to the right, and that's what's throwing it off. Okay. And what you'll see happen is that you're not going to have a normal distribution when you look at your histogram. It's kind of pushed off to the side. And notice that here, your mean and your median are in the same place. Whereas here, your mean is less than your median, and here your mean is more. Okay. So notice this whole time, the median, right, doesn't really move too much when you compare these. That's why we say the median is resistant to outliers. But those are just your different types of data. So it can be bell-shaped or normal or symmetrical, or it could be skewed left or skewed right.